will now look at a more significant non-trivial result about pushing maps of disks. And let me draw a simpler picture. Yeah, so while this will be used for CW complexes, this is about attaching disks. So to make it clear what we are talking about, let me just take a simpler situation. Here's the space, and to which I attach a disk. Okay, perhaps I attach a disk like this. And I have a path. And now what is evident is my path may happen to go over the disk or something. But if so, I can push it off the disk. Right? So I can push it off so that it goes only on the boundary of the disk. Namely, it's in the space to which the disk has been attached. And the important point about this path was that it's a one-dimensional object and the disk attached is a two-dimensional object. Okay, of course it's not true if the disk attached is an edge. So for example, I had a graph and it's not true up to homotopy, I mean, and I had, for example, this loop here, then it's not homotopic to something which can be pushed off this edge. So you can push lower dimensional objects off higher dimensional objects. This is the result that we'll use, and we'll use it inductively for maps between CW complexes. We can, but we'll first use it for maps from disks or spheres into CW complexes. Okay, so this is intuitive enough and it looks nice and easy, except that by this stage you're all very well aware that there are piano curves, they could be space filling. This purple one may not be this innocuous thing, it might instead go all around the disk. And so we have the same kind of technical issues that we had when we were showing pi 1 of S2 is trivial, or the Seifert-Van Kampen theorem, except it's a little worse here because the intervals are a little easier to deal with than higher dimensional objects. Okay, so this is not very difficult, but let's state things clearly. So suppose we have y is obtained from, let's say, x by attaching n disks. We can pretend only one, the argument doesn't depend on that, but let's say an arbitrary collection of n disks. We'll be applying it with arbitrary collections of n disks. So let's as well n disks along phi alpha. So in this case, of course, I mean phi alpha has to map Sn minus 1 to y to x. Okay, so we have this space. And now suppose we have a k disk where k is so let k be strictly less than n. For example, a one disk and a two thing. So we had an attached two disk and we had a path. So let k be strictly less than n, and let me say f maps dk to y such that let's say f of the boundary dk is already in x. Now x is a subset of y. Then theorem is that we can push this off. F is homotopic to G rel boundary dk with G of dk contained in x. Okay, so we'll apply this by saying that we have an n-1 skeleton if I have a n-1 disk, or a k disk in general for k less than or equal to n-1. It can always be homotoped fixing boundary to the n-1 skeleton, provided its boundary is already in the n-1 skeleton. So how we'll apply this is quite clear. And as we see inductively, we can say that if I have a map between CW complexes and the domain has dimension k, then we can push it into the k skeleton of the codomain. So that is the obvious corollary to this result. Our goal is to prove this. I am going to be rather sketchy in this proof. Okay, so let's pretend one disk was attached for the sake of the picture. Formally we'll have more. So idea is the following. We linearize f. So homotop f to, well, not really linear map, that's too much to ask for, to a map that is linear near the center, so 0 in dk. Okay, strictly speaking doesn't make sense. So we identify idea as homotopy, then note. Okay, once we have this linear, then just push off. Once we linearize it, we'll come to what we have to do next. So the key point is that we make it linear near these things. Okay, so let's sketch a few more details of this. So as usual, we are going to be subdividing. So we'll take, so I'm going to think of dk as a cube. Okay, so dk is interval, or for ambiguity, 0, 1 to the k, partly because this is what we are going to be applying it for. Okay, and let me draw a square here, and I'll partition it into pieces. It's not important, there are many ways of achieving this. And as usual, we are going to use Lebesgue number theorem. Okay, so let's just crudely subdivide this. Subdivide. And ensure by Lebesgue number that we want to say image has small diameter. But that's nonsensical because X is not a metric space. What we want to say is that if the image intersects is inside a cube, then it has small diameter. Okay, so let me be a little less stringent than that. We don't even need that. So here we have the disk. So by the way, this is the domain here that we have subdivided as a cube, not the attaching cell. So this is dk and this is dn. Okay, so inside dn, let's look at one little circle here. This is the core, and let's look like the earth, and I'll call this region the mantle. Okay, so you can apply Lebesgue number theorem by taking an open cover which consists of lots of little balls here, and then some balls which will intersect the boundary. Okay, such that, so we ensure by Lebesgue number theorem that instead of pointing out the cube, so what we ensure is that if I take any little cube here, okay, so let's call it a cubelet. For any cubelet, there's a little cube here. See what happens to f of c. So we are looking at f of c is either it's going to be disjoint from the mantle, so it's far away. This might mean it's completely inside X also. Remember, the disk is not everything. There's a whole lot of X sitting around. So the cubelet might go here, in which case we don't even try to control it. Okay, so the mantle is this middle region, which I'll shade in orange. So you're either disjoint from the mantle, okay, which is this middle region, or is fully in this disk dn, or more accurately some phi alpha of dn for some alpha here, and has diameter less than epsilon to be specified. Not actually going to specify it because, as I said, I'll be very sketchy. I will skip certain geometric details. So what we ensure is that if I look at the image of each cubelet, either it's going to be disjoint from the mantle, it's going to be contained completely inside X union this outer region. You can just take an open cover which contains X union some little annulus here and lots of small balls here, and apply Lebesgue number theorem to the domain to ensure this. Or you have an image which, if it intersects this mantle region at all, even if it overlaps like this, it must have very small diameter. Okay, and now we are going to only control things inside here. We are going to leave F outside alone. We are only going to control things inside the mantle region. So we modify f, which we can easily see is going to be homotopic to the original one. Okay, so no change on cubelets, whatever c, with f of c disjoint from mantle. Okay, so again here we have a cell. Actually we have a lot of copies of these cells, so we have lots of copies of these cells. All of them have, they're all copies of the disk, a core region, a larger mantle region, which is maybe spotted in this picture. Here there's a core region and a larger mantle region. Okay, and we have images which might be contained completely here and they go out also, in which case we don't try to control them, or they are small. So now they're going to be small enough in particular that they're not going to be intersect both the outside of the mantle and the core at the same time. When we make the geometry correctly, core is small, the mantle is bigger, anything here is small. Okay, so now we are going to linearize. What we are going to do is that I don't want a line, whatever it is black. So what we want is that if f of c is contained in what I'm calling mantle, that is this ball, then you replace f restricted to c by a linear map. Now this ball is convex, so what happens is if f of c is contained inside this, completely contained inside this, so it's a quite wild cube maybe, but it has small diameter. All its vertices are also contained inside the mantle region. They may hit the core as well, it might be here as well, but they are not outside. And so when I linearize, you get convex combinations of these, and that's also contained inside here. So this is going to be linearized. Okay, and then finally we have to deal with things that go across. Yeah, so if f of c intersection, whatever I call this mantle, is non-empty, but f of c is not contained in this. Okay, you extend by some convexity. So I'll try to be a little more clear in a moment. So what we do is, so there is one class of things that we can't handle. This picture is a little bit small, so I'll draw a blown up version of this picture. We have the core, which we don't care about. We have a rather large region, which is a mantle, which is a ball. It's round, so it's convex, by which I mean in the standard d alpha n, it's convex. We are attaching this standard disk. And then we have an image which goes like this and like this, and whatever the original one is, the new one is going to be a line here. It's going to be linearized here, and this is going to be whatever was the original one. So our problematic guys are the yellow, both these yellow parts which go from here to here, as well as the whole disk. Okay, so we do it inductively on dimension. Now a vertex is either going to be inside or outside, and so it's either going to be unchanged or linearized, but by the way, linearized is also unchanged, so its vertices are going to be unchanged. There is no problem. Okay, so now we'll turn to the edges. Now what could happen with an edge is that one vertex may be inside and one vertex might be outside, and so the previous map has been changed in one, unchanged in the other. Here it doesn't matter, but anyway, if it's changed in one and unchanged in the other, we will use a line to join these two, straight line to join these two. Okay, and now how about this disk? In higher dimensions it becomes more elaborate. This disk, things have got a little bit worse. It's now changed in part of the boundary, some of the edges, and it's not changed in this. So I'll take the center of these and just cone on it, take the convex. Okay, so by taking the center is not quite accurate. I just take a point which is close enough to the image of the disk, say inside the image of the disk, so that we don't end up wandering away. And then you could simply take the image of the midpoint itself of these, and then we extend by coning. on the boundary. So this is not linear. This part is not linear. It's a coned extension. But nevertheless, this does not increase the diameter. At least it doesn't increase the diameter by much. And crucially, these are disjoint from the core. Okay. Now, I'll just say new map. I haven't given it a name. Is homotopic to F. Why is it homotopic to F? Because all the changes have been made inside a ball. And so you can find a homotopy between, so you simply use a convex homotopy between F and the new map. New map, whatever I'll call it G, is homotopic to F. So you can take a convex, not homotopy, but homotopy between F and these, the new map. So we are now in good shape. What we have is we have something. So consequence, okay, so if, let me call the new of, if G of C intersection the core is non-empty, okay, then G restricted to C is linear. Fine. So that is because anything core is far, we have chosen small enough diameter, core is far enough from the boundary of the mantle, so that if G of C intersects, so these cross things are all here, anything that intersects the core will have all its vertices inside the mantle. And remember, if all your vertices are inside the mantle, you were linearized. Okay, so what does this mean? It means, hence, G of C, so not just G of C, okay, but the whole thing, G of the whole cube, 0, 1 to the power of k, intersection core, is contained in the image of k-dimensional spaces. And core is Bn. Okay. So now what you see is that if I take an image of k-dimensional subspaces, in fact there are compact subspaces inside K, compact subsets in k-dimensional subspaces inside an n dimension, and K is less than n, you must miss a point. So Bn minus G of 0, 1 to the K is non-empty. And up to homotopy, by using symmetry, without loss of generality, the center mu is not in G of 0, 1 to the n. You need not carry out this step, 0, 1 to the K, the image. Okay. So, well, why is this true, by the way? You can either hit it with a hammer, either you say that the image has measure 0 or bare category trivial, or you do a little bit of geometry. If you take subspaces of lower dimension, and balls in these subspaces or something, they can never fill up a ball in full space. So you have Bn, which is whatever 7 dimensional, you take subspaces of dimension 6 or 5 or something like that in this ball, or intersection of this ball will never fill up the ball. So you miss at least one point, and hence you miss these things. And now you use a radial homotopy like we did in the previous case. So you use a radial homotopy to push things. Remember that as soon as you miss the center, you can, the entire map misses the center, you can radiate out and push things out to the boundary. Okay, so this will complete the rather sketchy proof that if you if you attach n cells, any k-dimensional object, by which I mean specifically a disk relative to its boundary, as I said, inductively we can work with more general things, but if I have a disk relative to this boundary, can be pushed off an n cell up to homotopy.